Hello everyone, my name is Umberto Paggi and I'm a PhD student at KU Leuven in Belgium. The title of my research is Selective Laser Melting Process Strategies for Improved Part Precision and Feature Accuracy. But by looking at the literature, we can see that these terms are used to address a wide variety of situations depending on specific application, materials, and processes. So first of all, we have to ask, what are quality deviations? We can quantify and contextualize this concept in several ways. By looking at the whole part, for example, it is possible to establish if its dimensions are equal to the CAD model, if the final piece is homogeneously too big or too small, or if some warping or other local deformation had occurred. Alternatively, we can investigate the surface quality of our parts. In this case, the surface roughness value is often used to decide if a component is good or bad. But another important point is the surface homogeneity, which can be crucial in specific applications such as fluid transport. To solve these issues, samples are typically post-processed to achieve the geometrical tolerance and surface finish required. But this can be difficult and, most importantly, expensive. So my aim is to improve the existing scan strategy for a minimal need of secondary processes. Specifically, in my work, I will address two of the most common problematic features in the industrial reality: down-facing surfaces and shrinkage. For down-facing and overhanging region, the problem is the high surface roughness, which can cause a low accuracy for fine geometries and can result in a mechanical failures, for example in the screw, or in unwanted turbulence for the nozzle channels. For the shrinkage, issues arise when multiple behaviors are present in a single part. This can be caused by differences in structures, like the large cross-section of the bulk and the thin one of the lattice in the spinal cage, or in supporting condition, such as the attachment to the base plate of the nozzle opposed to the freestanding condition of its sides. These mechanisms are the main reason why a piece is out of tolerances and can lead to job failure if they are too extremes. A fair solution to the down-facing problem is a geometrical compensation in the XY plane. If we print a CAD model without any correction, the laser will scan the contour of every cross-section, creating a melt pool that extends over the intended size of our part. Therefore, we will produce a slightly bigger object. For this reason, an offset is applied which shifts the contour slightly inwards so that the final printed part is of the desired dimension. While for vertical surfaces, known as middle region, the offset is constant, for down-facing areas, this value changes due to the different melt pool behavior for different angles. Therefore, a series of down-facing samples were printed and measured to calculate the best offsets for angle between 25 and 75 degrees. Then, a benchmark with different horizontal compensated and non-compensated channels was printed and analyzed with a CT scan to reveal that all the compensated channels show a clear reduction in the deviation due to the down-facing geometrical error. The second proposed solution to the down-facing problem tackles the origin of the problem itself, which is the overheating of the down-facing melt pool and the powder bed. In this case, a contactless blade is printed just below the surface without touching it, in order to provide a quick heat extraction for the cooling process. This has been proven to work excellently for flat overhangs and low angle up to 15 degrees, and most interestingly, it was applied successfully on samples of increasing dimension up to 100 by 100 millimeters. This supporting technique can be implemented on difficult to reach areas, achieving not only a reduction in post-processing costs and times, but also an increase in freedom in the design phase, since orientation that were previously prohibited may now be printed. I would like to close this presentation with an overview of my PhD. The findings presented in this meeting are the result reported in the papers that I published so far. But even though this project is ending, other works are scheduled to be submitted next year, such as my collaboration with ESR1 on topology-optimized support structure for contactless supports, and the interpretation of the shrinkage results with ESR10 neural network. Here are the relevant publications mentioned before. If you have any question, you can contact me at the link below. Thank you everyone for your attention, and thanks to Anne and the PAM² project for this amazing opportunity.